Hi everyone. This is joint work with my advisor Shamanor, who's not here, and Huan Chu, who is. So the premise of the talk is sometimes we have a certain level of noise with which we can estimate whatever it is that we want to estimate. So if we have, for example, cat and dog pictures and we're doing classification, let's assume that problem is reasonably easy. So most of the time our error is near zero. And then there's another level of noise that occurs, for example, if we have label noise. So those are forced to be wrong, essentially. And then if what we're doing is ERM, then our loss and also the deviations of the loss might be dominated by these relatively few, say a few percent or tens of percent of larger noises. And then our sample complexity will scale polynomially with a level of maximal loss, essentially. So today we're going to talk about a version of another way of combining the multiple losses that is not ERM and that has loss which depends in that way only on some parameter beta that scales with the typical level of loss. So some level of loss that we can achieve for, say, 68% of the data. And only logarithmically with a level of maximal noise that we get for these outliers. We get that essentially by ignoring losses that are much larger than this beta, which is pretty similar to what happens to least trim squares, which is a robust estimation technique from the 80s. Our theory applies also to least trim squares, and we also show that for this new estimator we have linear convergence, so the algorithmic story is also better. Okay, so what do we do? What we see here is basically, what we see here is a weighted ERM. So these are weights, and these are the losses that we have for a model M over our data. And we scale this inner product so that this is an average, where W is uniform if it's 1. Okay, so the weights W are uniform when they're 1. And then the other thing we do is we regularize the weights that we use so that they're not too far from uniform. Okay? So the definition of our loss is gained by minimizing this W over all of this. Okay? So when W is say 1, this is just standard ERM, but we allow it to, for example, give 0 weight to some of the examples. Okay? And then an algorithm for minimizing this, which is pretty natural, is to just set the weights to minimize this term and then minimize the weighted ERM term that we have here. Okay? So what are some properties of this L beta loss? Basically, the step of finding the weights is very cheap. It's a projection of the vector of losses scaled by -1 over beta. So if we have some data and some 2 models, and these are the losses sorted for those 2 models, then we just invert those, multiply them by something, and we gain the weights. These are the weights. Okay? So what we know is that this is also always very easy to compute. In order to get nice properties, we need a little bit more than that. So if beta is such that some subset of our data, of size at least 2/3 of the data, has losses that are smaller than beta, in that case we gain nice properties. This W is near uniform in the sense that it's upper bounded by 2. So we said 1 is uniform, right? So we gave examples at most 2 times as much as we would in regular ERM. And another nice property is that when some particular loss is much larger than beta, say larger than 4 times beta, then the weight it will get is exactly 0. Okay? So this will prevent it from, on the one hand, dominating the weighted average of losses, but also it will protect us from it dominating the deviations. So we can show that it will concentrate. So I'll basically talk a little bit about the concentration theory, and if we have time also about the linear convergence theory, but we'll start with concentration. So what we want to show is essentially that this L beta will be close to its expectation with regard to taking a whole new sample of data from the same source. Okay? And we do that uniformly over some subset of models that I won't go into, but you can look at in the paper or in the poster. And most of it is pretty simple. We take a cover number argument. The complicated part is just to show concentration for a particular model. And the problem is that L beta is not a sum. So it's a weighted sum, and this W can change. So we would like to use something like McDiarmid and bounded differences, but basically in what we saw here, the only part that we know for sure is this, and this still allows for differences that are of the order of B. So that doesn't work. What that requires of us, in order to use all of these nice properties here, we need to use a version of McDiarmid that holds despite having the rare possibility of bad cases. So a bad case here is maybe for a different sample we could get all outliers, and suddenly all of our losses for this model are of order B, right? Luckily that is very improbable, since the number of losses under a threshold is highly concentrated, so we can use this type of concentration result that we at least learned about from Kuden. So as long as 2/3 of the losses are under beta, as we saw before, these weights are near uniform. The range of the losses that get non-zero weights, so that actually affect our inequality, is order of beta, and therefore the differences are bounded by beta over n. And this is basically what we need to get the concentration to be dominated by the typical loss levels and not the outlier loss levels. As a result, our bounds are dependent on the model that we find. If we find a good model, then we can use a lower beta and get tighter bounds. So that's basically the idea for the sample complexity, and we can see that essentially these ideas also apply to least trimmed squares, which we just ignore the larger losses. You have the same complications and the same solutions. So about the linear convergence, how am I doing this? So I'll do it quickly. Essentially, the projection step is a contraction. All we need to do is take a beta that is large enough to overcome some properties of the problem. So if this is large enough, then using the alternate minimization is a contraction, and it converges in a very small number of iterations. The problem with that, the nice part is that it founds a global optimum despite not being convex necessarily, but beta has to be large enough that outliers are given weight, which is not what we want. In a refinement of the analysis, we can actually restrict ourselves to a subset of the data and a subset of the models. For example, models that will uniformly ignore the outliers, so models which are approximately correct in the sense that we care about here. And in that case, the beta that we need only depends on those local properties of the problem for that A and for that subset of models. And in that case, we still get a contraction in M, and then we find an optimum which is the best available in M. So in particular, it can ignore outliers and still converge quickly. And that's it. That's all I want to say.
So questions for Daniel? Thank the speaker again.